Hello, welcome back to the wonderful world of physics. This is Chapter 3 homework for Physics 104A. We start with problem number 15. Use unit vectors to express a displacement of 120 kilometers at 29 degrees counterclockwise from the x-axis. So I recommend drawing a diagram as I did here. So we have an angle counterclockwise from the positive x-axis. You can see the vector. And the x component is r cosine theta, so 120 kilometers cosine 29 degrees, and that's 104.95 kilometers. The y component is r times sine theta, so 58.177 kilometers. The question says to use unit vectors, and so we take the x and y components and we'll say the r vector is 105, and here I've rounded off 105 I hat plus 58 j hat kilometers. Number 16, find the magnitude of the vector 34 I hat plus 13 j hat meters and determine its angle to the x-axis. Let's first draw a picture. 34 in the x direction, 13 in the y direction. We see then it's a quadrant 1 vector. We need the magnitude and the angle. Magnitude is given by the Pythagorean theorem. So 34 squared plus 13 squared, that gives 36.40 meters. The angle is the arctan of y over x, so 13 meters over 34 meters. We'll take the arctan of that and get 20.9 degrees. Now we always want to make sure that it fits the picture, meaning that we're in the right quadrant. And so we look back into the picture, it's a quadrant 1 angle. It looks about 20.9 degrees as opposed to being off in quadrant 3. And so we don't have to adjust by adding 180 degrees. So in the end, we have the magnitude and the angle. Here I've rounded off to the nearest digit. So r equals 36 meters and theta is 21 degrees. Number 21, an object's velocity is given there, and C and D are positive constants with appropriate units. What's the direction of the object's acceleration? So here I've written out the velocity vector. We want to know about the acceleration, so take the time derivative of each of those components. In the x direction, ct cubed becomes 3ct squared. In the y direction, the constant d, the time derivative, just becomes 0. And so the acceleration is purely in the x direction. And because it says that c is positive, then all of this is positive, so we can see the acceleration is in the positive x direction. And then because acceleration is completely in the x direction, we also know that the angle of acceleration is 0 degrees. It's completely horizontal. Number 25. An object is moving in the x direction at 1.3 meters per second when it undergoes an acceleration of 0.52 j hat meters per second squared. Find its velocity vector after 4.4 seconds. Here's the initial velocity vector. Here's the acceleration vector and the time. So for the velocity vector, we can use this kinematic equation that v equals v naught plus at. And here I've turned it into the stacked vector notation, so you can see the x and y component for v naught, the x and y component for acceleration, and then times time. Well, reading across the top for the x component, we get 1.3 plus 0 times 4.4, and that gives 1.3 in the x direction. Reading across the bottom, we'll get the y component, so 0 plus 0.52 times 4.4, and that gives us 2.288 meters per second. So putting it in unit vector notation, we get that the velocity vector at that later time, 4.4 seconds later, is 1.3 I hat plus 2.3 j hat meters per second. Number 30, The position of an object as a function of time is given by, and the book gives it in unit vector notation. Here I've written it in stacked vector notation. Find the object's acceleration vector. We take the position vector, and acceleration vector is going to be the second time derivative. So the first time derivative is going to give us velocity. We take the derivative of the x component, and we get 3.2 plus 3.6t. The derivative of the y component gives us 1.7 minus 4.8t. Now we take the time derivative of this vector, the velocity vector, to get acceleration. So the x component gets 3.6, the y component gets negative 4.8, and there's the acceleration vector. It is 3.6 I hat minus 4.8 j hat meters per second squared. Notice that it is not time dependent, it's constant. Number 33, a question of projectile motion. A carpenter tosses a shingle horizontally off an 8.8 meter high roof at 11 meters per second. How long does it take the shingle to reach the ground? How far does it move horizontally? It's important to note that it says he tosses it horizontally. That's going to make the math a little easier because the velocity does not have a y component. We don't have to deal with the trigonometry of an angle. We can just say that v naught is in the x direction, so v naught x is 11 meters per second. The question, well, it asks two questions. A, how long does it take the shingle to reach the ground? That's asking for the time. Here I've drawn the parabola, and so it's going to hit the ground here at some distance, we don't know. And we want to first solve for time. Once we have time, we can see how far does it move horizontally. I've set up the picture in such a way that down is the positive direction. I'm sorry, I've made down the negative direction. And so acceleration in the y direction is negative 9.80 meters per second squared. Y naught is 0. Because y downward is negative, y is negative 8.8 meters. We're going to use the vertical motion to assess the time. It's just as if, when we look at the vertical motion, just as if the shingle had been dropped straight down with a y initial velocity of 0. Because even though it truly is flying horizontally, remember from class that if something is shot horizontally or it's dropped straight down, it will hit the ground at the same time. So to solve for time, we'll use y equals y naught plus v naught yt plus 1/2 acceleration yt squared. Y naught is 0, v naught y is 0, and so all we're left with is y equals 1/2 acceleration times t squared. Solving for time, we get the square root of 2 times y times the acceleration in the y direction. Here I've plugged in the values and I get 1.34 seconds. Because the question is specifically asking how much time, I'm going to give that with two significant figures because that's what I'm limited to based on the given information. However, in question B, we're going to need that time, and I don't want to use the rounded off 1.3 seconds. I'm going to use, in question B, the full 1.34012 seconds. Now in question B, we assess the horizontal motion. X equals x naught, which is 0, plus v naught xt, plus 1/2 acceleration x times t squared. And remember, there is no acceleration in the x direction. And so that goes to 0. We're left with x equals 11 meters per second times the time, 1.34012 seconds, and we're left with 14.7 meters. And because we're limited to two significant figures, I'll round that to 15 meters. Number 34, another projectile motion problem. An arrow fired horizontally at 41 meters per second travels 23 meters horizontally. From what height was it fired? Once again, we have horizontal motion, initial horizontal motion. So in the x direction, we have the equation. Now this equation where my marker is started out as x equals x naught plus v naught xt plus 1/2 axt squared. But the x naught is 0 and the acceleration is 0, so this is all that remains of that equation. And we solve it for time. So time is the horizontal distance divided by the horizontal velocity, 23 meters over 41 meters per second, and we get 0.56096 seconds. Now we assess the vertical motion to find how far did it drop. Y equals, and we start with the long kinematic equation. I haven't written it here, but y equals y naught, which is 0, plus v naught yt, and the v naught y is 0 because there was no original vertical motion. And all we're left with is times 1/2 acceleration in the y direction times t squared. I've made down be negative, and so there's the negative acceleration. And we get y equals negative 1.542 meters, which means it dropped 1.542 meters. So we can say it was fired from a height of 1.5 meters. Number 40 is one of uniform circular motion. How fast would a car have to round a 75-meter radius turn for its acceleration to be numerically equivalent to that of gravity? Here we have the radius 75 meters, acceleration 9.80 meters per second squared. And we need to solve for velocity. So it's just a matter of taking the acceleration equation, a equals v squared over r, solve it for v, so v equals square root of ar, and you get 27 meters per second. Number 41, another question of circular motion, says determine the acceleration of the moon, which completes a nearly circular orbit. The radius is 384.4 megameters, and it does it in 27.3 days. So the equation we use is going to be a equals v squared over r. We're given the radius, and here I've got it in meters, 384.4 times 10 to the 6th meters. The period is 27.3 days. We need to convert that. You should get 2,358,720 seconds. And I recommend finding v from that information. For a circular orbit, the speed is going to be the circumference divided by the period. So distance over time, and we're contemplating one complete orbit. That's going to be the circumference divided by the period. And now, once we get that v, you could solve for v directly, plug in the numbers. I haven't done that here. Rather, what I've done is I've taken this expression for v and plugged it into the acceleration formula. So acceleration equals v squared over r becomes acceleration equals 2 pi r over t squared over r. I've cleaned it up a bit, so it's 4 pi squared r divided by t squared, and then I can plug in the given information r and t. And I get 2.73 times 10 to the negative 3 meters per second squared. Number 42. GPS satellites circle Earth at altitudes of approximately 20,000 kilometers, where the gravitational acceleration has 5.8% of its surface value. Now that means 5.8% of 9.80 newtons per kilogram, or meters per second squared. To the nearest hour, what is the orbital period of the GPS satellites? All right, so let's first find the acceleration. 5.8% of 9.80 is 0.5684 meters per second squared. Here I've drawn a little picture. There's the Earth. We have the radius of the Earth and the height. Now, in question 42, it says they are at altitudes of 20,000 kilometers. Altitude is my h that I've drawn there. That's not the radius of their orbit. That is the altitude or the height above the surface of the Earth. the radius of the circular orbit is going to be the radius of the Earth plus that height. So here I have radius of the orbit is radius of the Earth plus the altitude. We can find in the back flap of the book the radius of the Earth, 6.37 times 10 to the 6 meters, plus the altitude, 20,000 kilometers, which is 20 times 10 to the 6th meters. There we get the radius of the orbit. From question number 41, the previous question, I already derived this. Acceleration is 4 pi squared r over t squared. And let's solve that equation for t. You should get t equals the square root of 4 pi squared r over a. Let's clean that up a bit. The 4 and the pi squared can be taken out of the square root as just 2 pi, and we're left inside the square root with r over a. Then we can plug in all the values. You should get 42,796 seconds. We want to know what that is in hours, so divide by 3,600 seconds per hour and you get 12 hours. Number 48, fairly straightforward circular motion problem. An engineer is designing a flat horizontal road for 90 km per hour speed limit. The maximum acceleration of a vehicle on this road is 4.36 meters per second squared. What's the minimum safe radius for curves on the road? So we're solving for radius given the particular velocity. The one little thing we need to be mindful of, it says 90 kilometers per hour. And we know that in order for all the dimensions, the units to work out, we have to have consistent units. So we need this in meters per second. So convert that and you should get 25 meters per second. Then taking the acceleration equation, a equals v squared over r, solve it for r, you get r equals v squared over a, plug in the values and you get 140 meters. Question 49, very similar. Here we have designing a flat horizontal road with a radius of 125 meters in the curve. The engineer can count on an acceleration of at least 5 meters per second squared, provided by the tires of the vehicles rounding the curve. What should be the posted speed limit given to the nearest 10 kilometers per hour? So it's very similar to 48, but we're solving for v. So acceleration equals v squared over r gives us v equals square root of a times r. Plug in a and r, and you get 25 meters per second. Convert that and you get 90 kilometers per hour. Number 58. An object undergoes acceleration. It's given there at the top in 10 seconds, for 10 seconds. At the end of this time, its velocity vector is, and I've given it there, 33 I hat plus 15 j hat meters per second. 4 questions. What was its velocity at the beginning of the 10-second interval? All right, let's look at that one first. We're given v, we're given a, we're given time. Good setup for this kinematic equation, v equals v naught plus at. We want to know what the initial velocity was, so algebraically solve for v naught, and we have v naught equals v minus at. We're going to expand that into the stacked vector notation, so v is 33 and 15, the x and y components, minus the acceleration, there's the x and y components, times 10. Now, if you read across the top, that'll give you the x components of initial velocity, 33, minus 2.3 times 10, and that gives you 10. Reading across the bottom, that gives you the y components, 15, minus 3.6 times 10, that gives you negative 21. So the initial velocity vector was 10 I hat minus 21 j hat meters per second. Question B asks, by how much did its speed change? Now remember, speed is the magnitude of velocity. We have the original speed, which is, let's take those x and y components, we're going to use Pythagorean theorem, 33 squared plus 15 squared, and you get 36.249 meters per second. The initial velocity, so that top one was the final velocity, the initial one we just solve that in part A. 10 squared plus negative 21 squared, square root, and that gives 23.259 meters per second. The change in velocity is just the final minus initial. So we get that it increased by 13 meters per second. Question C asks, by how much did its direction change? Let's find the final direction. Theta is the arctan of Vy over Vx. And you plug those values in, you get 24.44 degrees. The initial angle, we do the same thing with the x and y components that we got from part A. So the y component is negative 21, the x component is 10, and we get an angle of negative 64.54 degrees. The change in angle is then going to be final minus initial, theta minus theta naught, and so it increased by 89 degrees. And finally, question D of problem number 58. Show that the speed change is not given by the magnitude of the acceleration multiplied by the time. All right, so written more mathematically, show that here I have delta V is not equal to A times T. Well, A times T is, and we need the acceleration magnitude. And up at the top in this box, we have acceleration. We find its magnitude by using Pythagorean theorem. And then we multiply by 10 seconds, and we get 43 meters per second. And we found in a previous part that the change in speed was 13 meters per second, and we see that they're not equal to each other. '64. A particle leaves the origin with its initial velocity given, and you can see I've written it there, undergoing constant acceleration given, and there I've written it. Question A, when, so we're solving for t, does the particle cross the y-axis? So if you imagine a Cartesian coordinate plane, if something is moving and it crosses the y-axis, that means that that's the point where x is equal to 0. So let's solve for that. We want to know time. We know the initial velocity. We know the acceleration. And it says in the problem that it starts at the origin. So x naught is 0. Y naught is 0 as well. And we want to know where x is equal to 0. So let's take this kinematic equation, fill in the given information, 0 equals 0 plus the x component initially of velocity, which is 11 times t, and then plus 1/2 of the x component of acceleration. Well, the x component of acceleration is negative 1.2, so we add half of that. That gives us minus 0.60 t squared. Solve that equation for t. First factor out t, and you should get two solutions. The first is t equals 0, and the second is 18.3 seconds, and I'm going to round that to two significant figures, so I get 18 seconds. Question B asks, what is its y-coordinate at that time? And so let's do it. We know the time. It actually came out to be 18.3 repeating seconds, and I'm going to use that more precise value down here. So y equals y naught, which is 0, plus we plug in all the values, v naught y and t, 1/2 y component of acceleration, which is 0.26 times t squared, and you get 300.4 meters as the y value. Part C says how fast is it moving and in what direction. Up at the top in the box, I've given the initial information from the problem, and we want to know how fast is it moving And so we can say v equals v naught plus at, and we're looking at the same time that we found that we're working with in parts A and B when it crosses the y-axis. And so we take v equals v naught plus at, there's v naught, 11 and 14, there's your acceleration, times the time of 18.3 seconds, and you get a velocity vector of negative 11 and 18.76 repeating meters per second. How fast? We take the magnitude of that vector by using Pythagorean theorem, and I get 22 meters per second. Part C also asks, and in what direction? So now that we've found the x and y component of velocity, let's find the angle by taking the arctan of Vy over Vx. Before I do that, I want to draw a picture. Look at the picture down here. I've drawn it based on these components. Negative 11, that means 11 to the left, and up 18.76. So it's a quadrant 2 equation. We're going to need that picture to assess what the arctan gives us. So we take the arctan of the Vy over Vx, and we get negative 59.6 degrees. It's then appropriate to look at the picture and see, does this match up? Well, negative 59.6 degrees is 59.6 degrees down from the x-axis. That's down here with my dotted line. Our vector that we're investigating is completely off by 180 degrees from that. So when you get this situation, just fix it by adding 180 degrees. So negative 59.6 plus 180, and then I did rounding off to the nearest degree, comes out to be 120 degrees. Question number 80 says, in the 2015 film The Martian, astronauts ride the Hermes spaceship between Earth and Mars. To help keep the astronauts' bodies in good shape on the long voyage, Hermes rotates to simulate Martian gravity. If the spacecraft's maximum diameter is 38 meters, what should be its rotation period, the time to complete one rotation, if the acceleration at its outer edge is to equal the gravitational acceleration on Mars? Well, we can look up in Appendix E planetary data, and it tells us that acceleration on Mars is 3.7 meters per second squared. We're given that the diameter of the spacecraft is 38 meters. We're more concerned with the radius, so half of that, 19 meters. And we want to find the rotational period. Well, we know that for circular motion, acceleration is v squared over r. And we can solve for v, given that we know r and a. But the question doesn't ask for what is the velocity. The question asks what is the rotational period. So we need to relate v to the rotational period, and here it is again, that the time for something to go around in a circle is the distance over the speed. So circumference divided by v, 2 pi r over v. Now, in the line above, I already solved for that v is square root of ra, so let's make that substitution. The period then is 2 pi r over square root of ra. We'll clean that up a bit. 2 pi, and then it's times the square root of r over a. We can then plug in those values, and we get 14.2 seconds. So in order to mimic Mars's acceleration, at least if you were standing right here on the outer edge where my pointer is, where the acceleration vector is drawn, then if the spacecraft rotates in 14.2 seconds, that would mimic Mars's gravity. That is the end of the Chapter 3 homework. Have a great day.